Next, we're going to look at more polar graphs. Here we're going to look at roses. Roses look completely different and we graph them completely differently from limicons. So again, take good notes. I'm going to work right through here. So if you need to pause to fill out your notes, that's fine. So roses have things we call leaves. I don't know why they don't call them petals. They look like petals to me more than they do leaves, but mathematicians for some reason call them leaves. So on roses, the graphs take this form. We still have r, we still have theta, we still have cosine and sine, and we only have a. A is the coefficient to cosine n theta and the coefficient to sine n theta. Now we have this new variable n, and n plays a role here that we have to pay attention to in roses. N leaves on a rose when n is an odd value, and there are 2 n leaves on a rose when n is an even value, 2 or greater. So what A represents is the distance from the pole to the tip of one of the leaves on the rose. Sine and cosine play a role that's not as straightforward as the role that it played in limicons. So sine and cosine in the equation help you to determine whether one or more of the leaves might, and might is a big word here, lie on the x and y axis. And the more of these that we graph, the more it will become clear to you what the form of the equation of the rose is going to tell you about whether you intersect the x or y axis. So here in general, we'll just graph the general with a being some value, some real number value, some integer value, cosine of 3 theta. So here n is odd, and I should expect to see 3 leaves on this. All right, so here we are. Here is exactly what this means. A represents the distance from the pole to the tip of a leaf. So this is this is A, goodness, this is A, and this is A. Now, there are no tick marks on the graph, so I don't know what the value of A is, but I know that I have A cosine of 3 theta, and I'm going to have 3 leaves. Not really sure whether one or more is going to lie on the x or y axis. I might be led to believe that because it's cosine, that one of those leaves would lie on the x-axis. We'll see if that bears out when we look at sine. So n equals 3. I expect 3 leaves. Now graphing these is a lot different than graphing the limicons, and we're going to graph one very slowly so you can see the process, but I want to look at another example. Here's one where r equals a cosine of 4 theta, where n is 4, so I should expect 2 times 4 leaves. I should expect 8 leaves on the graph of this. So since it's cosine, could I expect that one or more of the leaves might actually lie on the x-axis? So, yep, sure enough, I've got 8 leaves. There they are. On every single leaf, the distance from the pole to the end of the leaf is that distance A, whatever that number happens to be. And when we actually look at a rose where we have everything filled in, we'll have a value for A. So you can see here is a rose with 8 leaves. It turns out that 2 of them do indeed lie on the x-axis, but 2 of them lie on the y-axis and 4 of them lie out in the middle of the quadrants. So we really haven't determined yet the role that sine and cosine play. So let's look at one with sine involved. We're back to an odd number of leaves. I should expect to see 5 leaves on this graph. Might one or more of them lie on the y-axis? And sure enough, one of them does. So maybe a connection that I can make is when n is odd, I might expect that sine or cosine are going to play a role where one of the leaves is going to lie on that axis. For instance, when we saw a cosine of 3 theta, 2 of the leaves didn't lie on an axis, but one lied on the cosine axis. And here I have a times the sine of 5 theta. 4 of those don't lie because n is odd. 4 of those don't lie on any of the axis, and the only leaf that does lie on an axis is indeed the y-axis. So again, in our work, when we do homework, we'll see if that bears out for us. So here is r equals a times the sine of 2 theta. I should expect to see 4 leaves, and let's see if that has anything to do with the fact that any of them are on the y-axis. So here we are. Uh-oh. So when n is even, sine and cosine are not behaving like it does when n is odd. So let's just make sure that we again understand the role that A plays is it's the distance from the pole to the end of all the leaves. All of those are a distance. This very last point out here is a distance of A. So the best way to determine the graph of a rose is to actually pick theta values, plug them into your equation and find the corresponding R value and then plot those polar points in the plane and then connect them, understanding what a rose looks like. So let's graph R equals 2 times the sine of 2 theta. So I should expect the distance from the pole to the end of each leaf, and I should have 4 of them, should be a distance of 2. So let's see how we go about doing that. So to draw it by hand, I'm going to find a few values of R by using some exact values of theta that I have from trig. So I'm going to use the equation. I'm going to plug those theta values in, and I'm going to find the corresponding R value. Good values are those exact values. I'll start at theta equals 0. So when theta equals 0, I have 2 times the sine of 0. Well, the sine of 0 is 0, so R equals 0. So that's the point right here at the pole. That's the point I'm going to get when theta equals 0. Now, I could go up here and see what happens when theta equals pi over 6. Again, from what I know about the exact values table. So 2 times the sine of 2 times pi over 6 is pi over 3. The sine of pi over 3 is 1/2, so I should expect that to be the distance of 1/2 in the plane, and I can see that it more or less is. And then let's pick theta equal pi over 4. I'm going to plug that in. 2 times the sine of 2 times pi over 4 is where they get the sine of pi over 2, and that equals 1. So when theta equals pi over 4, R, the distance from the pole, remember R is always the distance from the pole, R equals 1. And then I know right here I'm at the end of a leaf, I know that that distance should be A. So we can continue going around our unit circle, plug those theta values in, find the corresponding R values, which is just the distance from the pole, and we can very clearly go ahead and draw all of those leaves. And so here is R equals 2 times the sine of 2 theta. So there's much more work involved in graphing a rose than there is graphing a limacon, and this depends heavily on our work on our exact values in our unit circle from trigonometry. So just in general, I won't take time to tell you where all of these values come from, but they do come from the fact that we're going to pick those exact theta values and we're going to plug those in and we're going to find corresponding distances from the pole. We're going to graph those points and then we're going to connect them, recognizing that we should have this many leaves. If n is odd, we should have n leaves. If n is even, we should have 2 times n leaves. So, and here are just some graphs. There's R equals the sine of 5 theta, where we know A is 1, so there should be 5 leaves. Here R equals the sine of 6 theta. N is even, so I should expect 2n or 12 leaves, and A is 1, so the distance from the pole to the end of all those leaves should be 1. The question is do any of them lie on the axes? Do none of them lie on the axes? That's why we just can't take off and graph any old thing that has 12 leaves, because sine plays a different role. R equals the cosine of 6 theta. Those 12 leaves are going to be there, but they're going to be in a different position. So we'll bear that out when we practice these roses in class, and so we're going to make sure that we know our unit circle. Bring that with you if you need to, but the more we do it, the more practice you'll understand. So roses are going to be a little more time intensive to graph than our limacons were. So come to class next time and we'll practice graphing some rose polar equations.